Okay, so it's very small. Can you put the first slide?
I will share another.
Okay, it's okay now.
Fine?
So this is page 2. So you should put, yes, that's right. So is it big enough or?
Yes, it's correct. It's perfect. Yes.
It's correct.
Then just tell me when you want to stop to go.
Yes, I will
to the
just
next page.
I will just tell next, please.
Okay.
All right. Thank you very much, Wissem, for the invitation. And I'm happy to see you again. I don't know where you are presently. You are in Riyadh or in Tunis? In Riyadh, right?
Yeah.
Yes. All right. So this is a talk about some of my recent papers. 2 of them have been written with Rui Ferreira and Stefan Gerhold. And there is also one of them I wrote alone. So it's excerpts from 3 different papers, and the papers are more general than that, but I have gathered the common theme, which is the Mittag-Leffler function and the Mittag-Leffler random variable. So you can put the next slide with them. So this is based on a very classical spatial function, which was introduced by Gustav Mittag-Leffler more than 100 years ago, so which bears his name, and it's written down as a convergent series. There is one parameter alpha. The parameter could be complex, but we choose it as a positive number. So the fact that the parameter alpha is positive makes the series convergent on the whole complex plane. So the series is very simple. And when alpha goes to 0, the function is hyperbolic function, and it is defined only when the real part of z is strictly smaller than 1. Whereas when alpha equals 1, then we recognize the exponential function. And therefore, for this reason, the Mittag-Leffler function is often viewed in the literature, old or recent, as a possible generalization of the exponential function. So when alpha equals 0, you recognize E0 of z as the moment generating function of the standard exponential random variable with density e to the power minus x on R plus. When alpha equals 1, then there is also an underlying random variable, which is simply the constant 1. So one question which is understood, which has been understood for many, many years, but this is an introductory file, is whether the Mittag-Leffler function is a moment generating function. So if you take alpha strictly greater than 1, and if you rewrite the
Thomas, can you reactive your microphone?
Yes, I have reactivated. Is it okay?
It's okay, yes.
So I was saying that when alpha equals 0 or 1, there is an underlying random variable. And I was also saying that when alpha is strictly greater than 1, then there is no such random variable, because if this random variable did exist, then factorial n divided by gamma of 1 plus alpha n should be an integer moment, and it is not the case by the Stirling formula. So subsequently, we will mostly consider the case where alpha belongs to 0, 1. The cases alpha equals 0 or alpha equals 1 being, explicit. Can you put the next slide, Wissam, please? What I did not understand is that I have to admit that someone, so I say yes. I'm not the administrator of the, all right. So let's consider now the case, the Gaussian case, where alpha equals 1/2. Then you can rewrite the quotient of factorial n and the gamma function by the Gauss multiplication formula on the gamma function. And then you recognize the square root up to some multiplicative constant of the gamma random variable with density as written down on the file. So 2 times this square root is also square root of 2 times the absolute value of the Gaussian random variable, or the standard Gaussian. So for this reason, which is extremely classical and known by Mittag-Leffler actually, you have an underlying Gaussian process. More precisely, you have the absolute value of Brownian motion lying behind. So the supremum of Brownian motion is also lying behind. And we can also recognize integer moments in the rational case when alpha is p divided by q, with q strictly greater than p. Then you can expand the quotient of gamma functions by the Legendre-Gauss multiplication formula on the gamma function, and you find some random variable to the power 1 divided by q, which is a product of beta and gamma random variables. For example, as this has been written down by Williams, but was actually known by various authors before that, when alpha is the reciprocal of an integer, then the underlying random variable is a product of q minus 1 gamma random variables to the power 1 divided by q. Thank you, Wissam, for the next slide. So, and of course, when alpha is not rational, then you can approximate, use a weak limit, and show that for all alpha between 0 and 1, there is an underlying random variable, which I will call m alpha, whose moment generating function is the Mittag-Leffler function. Probably it's not written down on the file. The person who did notice this for the first time was Pollard, or Pollard, I don't know how to pronounce it correctly in English, in the late 40s on a famous paper about the completely monotonic character of the Mittag-Leffler function, which is very well known by people using the Mittag-Leffler function. It was in 1948, and it was parallel to that, Feller did some work on the positive stable density, which is connected to the Mittag-Leffler random variable and to the Mittag-Leffler function. So I will consider this random variable, which is defined by its moment generating function. And also I will consider the fractional moments of this random variable, which are given by definition as a quotient of 2 gamma functions. So these fractional integer moments are defined on a half plane, on the right half plane. The real part of S should be strictly greater than -1. And you see there are simple poles. Well, at S equals -1, -2, -3, etc. So you can invert that by is the inverse Fourier transform or the inverse Mellin transform. This is the same, and you get an expression of the density of the random variable as a series, as a convergent series. So when you look at that, it's not clear that this function is positive, but it's true because it's the inverse Fourier transform of, or Laplace transform, anyway, of a moment generating function. You can notice that this series has a double alternating character. The first alternating character comes from the -1 to the power of n, and the second one comes from the gamma function on the denominator with a minus. So the sign of the gamma function also alternates, but not as regularly as it is the case for -1 to the power of n, of course. And you can also recognize, lying behind, a so-called right function, which I did not define on the side because, I want to focus on this case. But everything I'm telling you about today could be reformulated in a more general framework, in the two-parameter framework of right functions. Below, I have also plotted two curves, which is the shape of the density. So this is one of my subjects of interest. I like to study densities in a fine manner. So this will be the case in this talk, actually. So when alpha is smaller than 1/2, you have a decreasing function. And when alpha is strictly greater than 1/2, you have a unimodal density, which starts increasing and then decreases with a unique mode. So thank you, Wissam, for the next slide. So this random variable appears in several contexts, which are very classical, but maybe you do not know all of them. I will start with the most well-known one, which is the first passage time of a very classical stochastic process, which is the alpha stable subordinator. So if you take the alpha stable subordinator with a certain normalization, as written on the slide, which is a standard one, this is a strictly increasing process, which goes towards infinity as t goes towards infinity. So it crosses 1, and the time where it crosses 1 is actually distributed as a Mittag-Leffler random variable. Another very classical occurrence is when you take alpha greater than 1/2 and beta 1 divided by alpha. So beta is between 1 and 2. Then you have a Levy beta stable process, without positive jumps, with a normalization, which is given on the slide. So this is also the standard one. Then M alpha is distributed as the supremum of this process up to the running supremum up to time 1. And it is also distributed as the random variable Z1 itself, but conditioned on being positive. So this is a cutoff random variable. You just look at the positive part of the density, at the density on R+, at the restriction of the density on R+. So this was known by the Russian school in the 50s. I think this was first proved by Skorohod in 1950, at the end of the 1950s. Now, something which is a bit more intricate is, well, you still consider the stable subordinator, and you consider the process of its passage times, which means that you index the random variable M alpha actually by some level. So you consider the first time the stable subordinator crosses S, and you let S vary between 0 and 1. So you have something like a devil's staircase, which is stochastic. It's a devil's staircase because the stable subordinator always jumps, and so the inverse process, which is written down, it has always some plateaus where it stays constant, but still it increases. And so the Lebesgue measure of the increase point is 0, but this increase point has a fractal structure, well, which corresponds to the fractal structure of the subordinator itself. But what is interesting is that if you consider this, what I was talking about, the points of increase of this table staircase, then this is also distributed as the zeros of a Bessel process with a certain index, which is d equals 2 times 1 minus alpha. So the zeros of a recurrent Bessel process. And it is also well known that if you consider the local time process of this recurrent Markov process, the Bessel process of dimension between 0 and 2, then up to some normalization, which is written down in the red box at the bottom end of the side, you recognize again the Mittag-Leffler random variable. So next slide, please. So now I wanted to mention another occurrence of the Mittag-Leffler random variable, which is less well known probably. The connection is made with a certain integral differential equation, which generalizes or actually interpolates between the standard heat equation, which corresponds to the case alpha equals 1/2, and the wave equation, which corresponds to the case alpha equals 1. So this is a very simple integral differential equation. And the solution, the unique solution, when you have an initial data which is integrable enough, it's simply sufficient that it integrates the Gaussian kernel. Then the time-space solution of this integral differential equation is given as a sort of, well, it really looks like D'Alembert's solution to the wave equation, but it is expressed in terms of an expectation of a process involving, well, 2 copies of the Mittag-Leffler random variable. So this was observed by Fujita in a well-known paper. And so you have something which really looks like the solution to the wave equation. But if you look at the case alpha equals 1/2, then you have the sum of the positive part of the Gaussian and of the negative part of the Gaussian. So if you merge the two, so you find again the Gaussian random variable actually. So there are other occurrences of the Mittag-Leffler random variable. They are numerous enough to deserve a survey, which was written down by Huillet 6 years ago. And for generalization of this integral differential I was just mentioning, you should look at the book by Gorenflo, Kilbas, Melardi, and Rogozin, who are interested in physical interpretations of this random variable. And the physical equations lying behind look like or are generalizations thereof the integral differential equation of Fujita. Next slide, please. So now I want to present some of the results I have discovered on this function and on this random variable. So I wanted to present the result abruptly and then discuss it. So I am interested in so we have seen that the density of the Mittag-Leffler random variable is always unimodal. When alpha is smaller than 1/2, it is decreasing, and when alpha is greater than 1/2, it is increasing, then decreasing. This is not absolutely trivial to prove. It goes back to the Russian school, and it was the first step in proving that the stable densities, which are more general objects, are all unimodal. And it was a problem which took some time to be settled in the 70s finally by Yamazato. But what actually Yamazato used is the notion of log concavity. I will explain later why log concavity is important for unimodality, but it's very easy to see that log concavity is the generalization of unimodality, because the quotient of the logarithmic derivative should decrease, so the derivative itself should change its sign at most one. And so the first result I want to present is a characterization of this property, the log concavity, for the Mittag-Leffler random variable. And it is expressed in terms of a certain parameter, which is implicitly defined as a solution on an equation on the gamma function. And the value, the approximate value, is also written down. This approximate value has some importance for the proof, but it's a bit technical to explain why. And what this parameter also characterizes is the reciprocal convexity of the Mittag-Leffler function on the negative half line. If you consider, this is the result. I will give some hints on the proof after. I want to mention that for the reciprocal convexity of the Mittag-Leffler function, it is always true for all positive. I'm sorry, there was a question or remark? Okay, maybe this was some noise, so I should go on. So if you consider the property on the positive half line for the reciprocal convexity of the Mittag-Leffler function, then it is always true. It is not absolutely, it is not immediate, but it's much easier than the property on the negative half line, because all the parameters and all the variates are positive. So you basically consider a series of positive series, and the ratio of positive series is a common topic on special function, especially on Bessel functions. And there is a classical lemma which is always used even nowadays by Biernacki and Gzij, which makes it possible to analyze quotients of positive series. But of course, this does not work anymore when you consider the negative half line, because you have an alternate. You have a series with which alternates in sign. A motivation. I go back to the first property, the log concavity of phi alpha. So I was saying that it is a natural and classical generalization of unimodality. But one motivation is also the aforementioned integral differential equation, because there is a classical theorem by Ibragimov, which was used by Yamazato in his proof of the unimodality of stable density, which says that if you consider the notion of strong unimodality means that if you make the convolution of the independent sum of a unimodal random variable on a strongly unimodal random variable, then it will remain unimodal, because unimodality is not stable under independence addition in general. The theorem by Ibragimov tells you that this is a characterization. This means that if you consider the addition of a unimodal random variable and another random variable, the sum will remain unimodal if and only if the random variable is strongly unimodal. In other words, if a random variable is not strongly unimodal, then there might be, and still unimodal, its sum with another unimodal random variable might not be unimodal. So this is actually the important part in Ibragimov theorem, because the if part, that log concavity preserves unimodality, is actually a variation on the notion of total positivity of order 2 and is older than Ibragimov theorem. Anyway, if we use this theorem in its full force, I mean the characterization of log concavity as a strong unimodality property, then you can apply it for the solution of the previous integral differential equation and see that if the initial data is unimodal, then the property will be preserved in each factor of the sum, which means that the solution which will be the superposition of two unimodal signals. If and only will always be like that, if and only if alpha is smaller than the critical parameter, alpha star. Okay, you can put the next slide, please, Wissam. So I want to give you some ideas on the proof because, well, one reason is that Wissam knows this factorization I am mentioning at the beginning of the slide because we worked on this together some 5 years ago for another problem. And so this is the possibility to factorize M alpha as the terminal value of a certain multiplicative martingale, which is constructed as simply as the independent product of random variable with positive random variable with expectation 1. So if you look in the product at k plus 1 divided by k plus alpha, this is the reciprocal of the expectation of the beta random variable written down just after that. So you are making the independent product of random variable with expectation 1. So you are taking a positive martingale, having a multiplicative form, and so it converges. And you can identify the positive moments of this limit up to the prefactor, which is 1 divided by gamma to 1 plus alpha. And it turns out that it is simply the integral moment of M alpha. And we know that M alpha is characterized by its integral moments because it has a moment generative function, which is defined on the whole complex plane. And so you can have this identification. As I said, I knew that well, we had used the same factorization in the paper with Wissam, but we derived it differently. I think that the positive martingale point of view is maybe the most direct one. So we have decomposed our random variable of interest in terms of factors which all have an explicit density, so we can analyze these densities. And when alpha is smaller than 1/2, then the 1 alpha minus 1 of parameter of the beta random variable is greater than 1, which means that this beta random variable will itself have a log concave density because I minus 1 minus x to the power c is log concave if and only if c is positive, because if you take the logarithm, you have a c times logarithm of 1 minus x. So it's as simple as that. But then things become a bit more complicated because we have a product. We do not have a sum. If we had a sum, then we could use the celebrated Prekopala-Hindler theorem, which tells you that the convolution of two log concave functions remain log concave. This is a very important result. But here we cannot use it directly because we are making the multiplicative convolution. So to be honest, I was stuck on this problem for a certain amount of time. As happens quite often, the solution is not very difficult, but it took me some time to find it, is to take the reverse martingale. If you take the reverse martingales, the computations are smooth. And you can use the Prekopala-Hindler theorem again and again and find what you are looking for, what I was looking for, which means that for this case, the product acts in a certain way as a sum. And so you use the fact that all factors have a log concave density and you get what you want. If you take alpha greater than 1/2, then you cannot use this argument because all factors have not log concave density. So what I use is what I was mentioning at the beginning of the talk, is that lying behind you have a stable density, a real stable density. And those densities are self-decomposable. So self-decomposability means that they have a certain, well, they are infinitely divisible, and lying behind the infinite divisibility is another integral differential equation. And this integral differential equation is linear. And so you can play a bit with it and show, this is what Sato and Yamazato did some time ago, that after the mode, in this case, you get what you want. The density is log concave. So this is true for all alpha greater than 1/2. So we need to study the property and between 0 and m, which is a mode, the positive mode of the underlying stable random variable. So again, this took me some time to get the solution. And I was very fortunate well, actually to have been involved in that, but the answer was given by Kwasniewski, my colleague, which proved the fundamental property of the stable densities, which was open for some time, which is called the bell shape. Bell shape means that the nth derivative of the density vanishes exactly n times. For stable densities, to prove that the first derivative vanishes once is the unimodality. So it is a known fact. It had been known for something like 45 years. But even the simple visual fact that it has two inflection points, which means that the second derivative vanishes only twice, is not at all a trivial problem, but it was proved by Kwasniewski. So 3 years ago. And so if you consider the case where alpha is smaller than 2/3, then you know that the second derivative at 0 is negative. If it is negative, it should stay negative up to the mode by the bell-shaped property, because the second derivative is also negative at the mode. And then it is positive. And at the beginning, it is positive. So between 2 points where the second derivative is negative, it is always negative. Again, I insist that it is not at all trivial for stable densities, but it is true. And so if it is concave, it is log concave. So you get what you want, and it is not difficult provided you have Kwasniewski's result. But then things become more intricate when alpha is strictly greater than 2/3. And so I skip the proof, which is a bit technical, and which uses, again, the bell shape, but at higher levels, more precisely at level 3 and level 4. And this is what I was mentioning at the beginning, the fact that the critical parameter is smaller than 4 divided by 5 is absolutely crucial, because if it were greater than that, the argument would not work. All right. So I can go to the next slide. Thank you, Wissem. So maybe I should skip this slide because this slide is about more simple parts of the proof, which are the other, we have a characterization. So this slide just means that you read off the property, the log concavity of the Mittag-Leffler random variable or the reciprocal convexity of the Mittag-Leffler function, either at 0 for the Mittag-Leffler random variable or at infinity, minus infinity for the Mittag-Leffler function. Well, maybe I can say something more, is that when I was working on this paper, I noticed a general result by Clark-Plagg and Lehec connecting the log concavity of a given density on R+ to the reciprocal convexity of certain power of certain derivatives of the moment generating function. And the fact is there is a characterization which is general. And here in our example, we only have a characterization with n equals 1. So this is something which is peculiar to the Mittag-Leffler random variable, but actually there is something more lying behind. And what was a bit puzzling for me is that everything is read off at infinity for the Mittag-Leffler function. I mean, the behavior, the convexity of these powers of the reciprocal convexity of these powers of moment generating function is always read off at minus infinity, actually. Okay, so next slide, please. So now I want to present another result, which is which deals with convexity, but the problem is very different. I am considering a notion of convex ordering between real and integrable random variables. So we say that a certain random variable dominates another one for the convex order. If, well, my son now has to go to school and he's making fun of me, but that's okay. If, well, you have two inequalities between tails of distribution function at minus infinity and the survival function at infinity. So these tails, the integral of these tails do exist because the random variables are integrable, of course. So this is a classical notion which is very well displayed in the book by Sheked and Shantikumar on convex orderings. And this amounts to, and this gives a name to this ordering, the fact that the expectation of psi of x is smaller than the expectation of psi of y for all psi convex such that the expectations exist. So of course, if you take up psi equals the identity or minus the identity, then you get the fact that the expectations are equal. So the convex ordering is something which measures the way, the dispersion of the relative dispersion of two random variables around the same mean. And it is some kind of second order ordering, the first order ordering being the standard stochastic order, where the expectation are the expectations are not the same. One expectation is greater than the other one. So if you are given this notion, you can consider a collection of integrable random variables indexed by an interval, I, and colleagues of mine wrote a book about a notion which they called PCOC. PCOC means processus croissant pour l'ordre convexe, PCOC, so PCOC, this gives the acronym PCOC. And it simply says that the collection is increasing for the convex order. In other words, if S is smaller than T, then XS is smaller than XT for the convex ordering. And if you go back to the Bessel process, which is associated to the Mittag-Leffler random variable, I was inspired by some literatures of the Parisian school on Bessel process and the normalization of the local times. So you have you can normalize the local time so that its expectation is 1. And you have a collection of random variables with the same expectation, which is indexed by alpha or by d, equals 1 minus d divided by 2, d being the dimension of the Bessel process. And of course, the greater the d, the less recurrent the process is. And well, I was puzzled by how order these local times. And the answer is given by the theorem written down at the end of the slide, that there is a peacock property for these random variables, which is indexed by the dimension. All right, next slide, please. And so there is a process, there is a Bessel process lying behind the Mittag-Leffler random variable. There is also, so the Bessel process is a Markov process. When you have a peacock, it is well known by users of this notion that lying behind there is a martingale. So it's given by a classical theorem by Kellerer. I wanted to mention that there is another martingale which is associated to another Markov process, which is also associated to the Mittag-Leffler random variable. The process is much simpler, actually. The process is built upon the multiplicative properties of the Mittag-Leffler random variable. And it is connected to some coalescent models. What I might say is that this martingale, which was introduced by Müller, has an additive character, whereas the martingale, which is associated to the peacock, is more multiplicative. So I want to give some hints on the proof of this property, because again, it uses a factorization we had considered with Wissem, which is the second factorization. So if you remember the proof of my previous theorem, we had a product of beta random variable to the power 1. And here we have a product of beta random variable to the power alpha. So these two products give the same variable. So they are, these two products are also limits, almost sure limits of a certain multiplicative martingale, but the martingales are of course not the same. What I can say is that these are the two only possibilities to get such terminal values. If you try to do the computations with other powers, the beta variables I am considering are well ordered. I mean, the parameters are spaced according to some arithmetic subsequence. If you try to do something like that with other kinds of random variable, it does not work. And there is a reason lying behind this, which I noticed recently actually, is that lying behind there is a so-called perpetuity. But there are two factorizations. The first one works for this log concavity property, but it does not work for the peacock property. But fortunately, the second one gives you the right tool, because you can again work on each factor, as we did in the case alpha smaller than 1/2. And next slide, please. And then you have to work on each factor and to use a crossing property between densities of the factor. So you have to prove a certain decreasing property for the convex order. And if you work on it on each factor, then you basically compare two curves. Those curves are not comparable in the classic sense, but the important fact is that they cross only twice, and that there is a certain sign sequence, which is plus, minus, plus, or minus, plus, minus. It depends on how you compare your parameters. But the fact that these curves cross twice gives you the convex order you are looking for. And I think I will end this talk with the next slide, because I think I am almost out of time. There is a consequence of this convex ordering, which I found interesting. It's that if you go back to the moment generating function, which is a Mittag-Leffler function, and if you take a certain normalization, which is what I am writing down now, which means that you consider the Mittag-Leffler function at gamma 1 plus alpha z. You make a light shift, a light multiplicative shift. And the reason why you do that is that at 0, this renormalized Mittag-Leffler function has the same value 1, but also its first derivative. So we have a collection of functions which meet at 0 with the same derivative. And if you look at what happens as alpha goes to 0, then you get an hyperbolic curve. And if you look at what happens as alpha goes to 1, you get an exponential curve. And it's elementary to prove that the exponential is always below the hyperbolic curve. So what you can get with the convex ordering is a non-trivial fact for Z negative, that the mapping which associates f alpha of Z to alpha is monotonous, which means that the collection of curves are perfectly well ordered between the exponential curve and the hyperbolic curve. And well, my motivation is a bit that of someone looking at the internet, because if you look at the Wikipedia page on the Mittag-Leffler function, those curves are actually plotted, and there is some kind of dynamic, some GIF dynamic, and you see that the curve are monotonous. Well, I just proved it, and well, I was satisfied with that. So I think I will stop now. Thank you. Thank you, Wissam.
Okay, thank you, Thomas.
Yes.
Are there any questions, please? Hello? Yeah, everybody can hear me, huh? Right? Thomas, do you hear me?
Yes, I am. I hear you. Yes.
Okay. Then maybe I have a question for you. If you allow me, I will share again the slides. Okay. Then at the very beginning of the definition of the Mittag-Leffler random variable,
Yes.
I was wondering why you didn't notice immediately that M alpha corresponds to the power,
Well, of course. Yes. This is a way to build. This is what I was mentioning when I was talking about Feller's paper. This is what Feller did, actually. But this is just a way of considering this random variable. This is a way of building it. But of course, this is the negative power of the positive alpha stable random variable. This is true, yes.
Maybe it will unveil some of specification. Okay.
I did not get you.
Okay. Are there any other questions, please?
Salam. Yes, brother Wissam. Say Fathi. Hey, salut.
Okay.
Good afternoon.
Good
Thank you for a
afternoon.
nice talk, despite the interruptions and the inaudible voice sometimes. I just wanted to say one thing, because there is an author by the name of Zhao Jun Yang. He's got a few conjectures about Mittag-Leffler that might interest you, because it's probably close to your work. I will try to send you the if I get your email from Nabil or from yourself in the chat or something, I will try to send you the latest of his work, because he's putting them in my group, in the PAM group. So if you would like to get that, I just need your email, Thomas. Best.
Well, maybe you can ask Wissam, because
Okay.
Yeah. Yes, I will do that.
But anyway, if you want to, I am interested, of course, in what you are telling now. You can just Google me and put Lille, which is my university, after my name, because there are many Thomas Simon all over the world making all kinds of jobs. The most crazy ones. But if you put Lille after my name, then you will get my page and you will get my email address.
Mumtaz. Très bien. Very good. Very good. Thank you. Thank you.
But, you can also ask Wissam. But thank you for your comment.
Very,
Oh, now I do not
like
hear.
the slides that Wissam has, if possible. You don't hear me? Okay. I would like.
Yeah, no, I hear you. I can send you my
slides.
slide as well, but you can also ask.
Yes.
Well, I can send you my slide if you write to me.
Please check the chat and take my email there, please.
All right. So I have the chat. All right.
Yeah.
Okay, but yes, I will try to check the chat. Okay.
Or Wissam can send it to you. Yes.
I will send you his email address. Don't worry.
Thank you very much.
Thank you.
Thank you. Most welcome.
Okay. I also have another question, if you allow me.
Vas-y.
I've seen a nice lemma, this one. Then for the Mittag-Leffler function, you have this equivalence only. The equivalence holds with n equal 1, right?
Yes. But that was a bit surprising, because it is true for all n. It is true for all n. So, for example, if you take n equals 2, then you get the derivative of the Mittag-Leffler function, which is another Mittag-Leffler function. It is the E alpha alpha. And yes. E alpha alpha, it is interesting because it is the kind of ground state. Well, it's a terminology which is a bit over the top, but you have a two-parameter Laplace function, right? You have E alpha beta. You are following me, Wissam? And yes, you know that beta equals alpha is the smallest possible parameter to get something probabilistic lying behind. And this is interesting because at E alpha alpha something there is a kind of jump in the behavior of the function. So the behavior of E alpha alpha is not the same as E alpha beta with beta greater than alpha. So I was a bit puzzled by the case alpha equals 2, but it works actually. It is also true by this general result. By this general result. So if you use this general result, of course, what is hard, in my opinion, in the first result I was mentioning is to get the first equivalent, right? Because the second equivalence, you can use this general result on the one hand and the asymptotic on the other hand. But you can also get a direct proof with the lemma by Biernacki and Gjij, and I gave it in the paper. But again, there is something more general lying behind, and which was a bit surprising to me.
Right. And do you have complete monotony properties for 1 over alpha?
Yeah, of course, this general result by Clartag and Leek is a complete monotonicity property. And I know you are very fond of the book by Schilling, Song, and Vondracek. And I think you are also fond of Hirsch's class, the so-called Hirsch class with log-convex potentials. And this result is actually a kind of well, in Hirsch class, you have log convexity, and in this class, you have log concavity. So those results are connected, at least in a formal way. But the recent result I was mentioning is actually more difficult. Is harder than the class by Hirsch. But there are some formal similarities. You just you have a series where the x to the power of n is replaced by minus x to the power of n, and you have a function where log convexity is replaced by log concavity. And in both cases, you have either absolute monotonicity or complete monotonicity, something like that. But I can send you the reference if you want. But in this case, for the Mittag-Leffler functions, I was surprised by well, I think now I understood all of it, but at the beginning I was a bit. I was not expecting that something more general was happening. Anyway. Because of the case n equals 2.
Yes.
I think I sent you the paper, right, with Sam? I sent you the paper.
No. Okay. Are there any other question, please? Okay. In this case, we would like to thank
you,
Thomas.
Thank you.
Thank you. Thank you, Thomas.
Thank you.
Thank
Bye-bye.
you. Thank you, Nabil. Thank you, Thomas.
On devrait continuer on devrait se faire quelques zooms de temps en temps.
Et si tu veux, on peut rester là. T'es dispo là?
Ah non, ça c'est le zoom de Nabil. Donc.
Mais
envoie-moi ton téléphone. Des fois, on pourra.
Envoie-moi ton téléphone si tu veux et on peut se faire un WhatsApp, un de ces quatre.
Ou un Zoom, c'est encore plus sympa.
Mais non, moi justement, Zoom, ça marche pas très bien parce que à chaque fois, mon ordinateur. D'ailleurs, demain, je fais un cours en ligne et je sais que je vais être obligé je sais pas, ça marche pas toujours très bien. Enfin, bon, écoute, tu m'envoies ton téléphone et puis on peut se faire un WhatsApp, si tu veux.
Ok, ça marche. Allez, porte-toi bien.
Ok, merci.
Toi aussi.
Bientôt.
À bientôt.
Merci.
Oui, je comprenais que vous étiez francophone aussi. Merci. Au revoir.
Au revoir.
Au revoir, merci. Bye bye.
فتحي، إلى اللقاء.
مع السلامة. ميرسي يا نبيل، جزاك الله خير. شكرا. باي.